I'm Antonio Sala. In this video, we'll discuss conditional uncorrelation and chain linear predictions, and we'll put forward a couple of examples. This will be a particularization of the issues of conditional independence when we are discussing only on how to make linear predictions. So if we review conditional independence, it meant that if I have three random variables, A, B, C, if once I know A, further knowledge of C helps nothing in estimating B, or conversely, further knowledge of B does nothing in improving my belief in C, then these values are said to be conditionally independent when A takes a given value, or well, if it's for any possible value of A, conditionally independent given A. Conditional independence allowed drawing some diagrams whose general form is called Bayesian network, so that we can express probabilistic models in a graphical way. However, at least in control, in many cases, we are interested in making linear predictions of some variables. Identification of linear models is of paramount importance. Also, statistical independence is harder to prove than lack of correlation, at least approximately. If I get a lot of data and I compute the mean of the product, if it is very low, I may say that these variables are uncorrelated and I cannot make linear predictions of one given the other due to the lack of correlation. So let us explore how the concept of conditional independence applies when we are just discussing linear predictions and conditional uncorrelation. So, as it is a relationship between three random variables, if we have a covariance matrix 3 by 3 like this, then this is the expression of the best linear prediction in the sense that the prediction error has lowest variance. The best linear prediction of B and C given A is this matrix theta, the constant predictor that multiplies the values that I observe of variable A if available. The prediction error variance has this formula. This is the a priori variance of B and C, and this is the reduction due to the knowledge of A. This covariance inverse of the variance of A and the covariance transposed. So we get this expression, and what we pursue in our definition is examining if this thing is zero or not. If this is zero, of course this is symmetric, so this will also be zero, then we will say that these variables are conditionally uncorrelated given A. What does it mean? Well, if this remaining correlation is zero, it means that once I know A, for instance, further information about B will be useless to improve my prediction about C, at least when I speak about linear predictions. Vice versa, further information about C will not allow me to give a better linear prediction of B, better than the one I already have. So this is the particularization of the conditional independence stuff to only conditional incorrelation when we wish to make linear predictions. So let us put some examples of these issues to better understand what we are talking about. The first example will be the sum of two random variables. So B and C will be assumed statistically independent, B variance 2, C variance 1, and A will be their sum. So to start with, we need to build the whole 3 by 3 covariance matrix. Of course, if B and C are independent, then this piece of the matrix is known, variance in the diagonal and 0, because independent variables are not correlated. Good. So we need to compute this piece of the matrix, which is the covariance between A and B. Well, as A is B plus C, then B squared plus CB. When I take expectations, as B and C are independent, this is 0, so I get the expectation of B squared, so variance of B. Then this is why these two copies in these two places by symmetry. Likewise, the covariance between A and C, doing this product will have zero correlation, zero covariance. So only the variance of C will remain. So this one copies here and here. Last, the variance of A, this element here, well, B plus C squared is the usual formula, square of B plus square of C plus double of the product. The expectation of this product will be zero because of the independence assumption, so I will get the sum of variance of B and C, and hence 2 plus 1 is the 3 I am putting there. So we have the 3 by 3 matrix to start with and discuss some conclusions on it. So now let us compute the residual variance of the best prediction given A. So information is the element 1, 1, 1, A, and then the variance formula gives me this residual variance. So if I know the sum, then this is what remains unknown for me. As it is not diagonal, then we realize that even if marginally, when the sum was not known, they were not correlated, they are statistically independent variables. Once I know the sum, suddenly a correlation appears. This is, of course, conditional correlation, negative. So if the sum is fixed, a large value of B entails a small value of C. Of course, this is common sense. In fact, if I compute the eigenvalues of this residual variance, I get this zero eigenvalue. So it means that in this 2 by 2 residual, there is still one source of randomness, but another source of randomness now has zero variance. So it is deterministic. Indeed, this is in accordance to common sense, in which, okay, if I know the sum of B and C, and I know, let's say, B, then I can compute C deterministically. I mean, if the sum is 5 and B is 4, then C is 1. Whatever the mechanism to throw B and C is. So this 0 means that once I know A, there is a deterministic component in the relationship between B and C, which, as I say, is just common sense. But this is a way to understand what these residual correlations, etc. mean. So we have two values that are uncorrelated, but conditionally correlated once I know their sum. Good. Let us now discuss a second example. In this example, I will have a 3 by 3 covariance matrix, but one of the numbers, I will leave them to test for different options as an adjustable parameter. So if this number, I put it to 0, then I get this covariance matrix. So I am in a similar case to the previous one. I have two variables that are not correlated, at least marginally, if I know nothing else. But the knowledge of a third variable, A, which is correlated with both of them, then introduces some interdependence if that additional variable is known. It's a positive definite matrix, otherwise it would be nonsense in statistical terms. Okay, so good. And then, as I said, this is 0, no correlation if A is unknown, but this is non-zero, so they get conditionally correlated in the same way as the sum stuff. But in this case, if I compute the eigenvalues, the correlation is not that intense in the sense that there are still two sources of randomness. So we have not reached the total determinism that we had underlying in the sum example. Now we will set the covariance between B and C to this value so that this is 0. In this way, we will get conditional uncorrelation. Let's see. If this value is 3 by 4, 12 divided by 2, 6, there is it, then we check that it's still a positive definite matrix. And then if we compute prediction error variance once I know the first variable, a, then this is diagonal. Of course, we crafted this value in order for this matrix to be diagonal following the above theory. So the variables b and c are correlated, but once I know a, they are conditionally uncorrelated, which means that if I know a, then the best linear prediction of b does not involve c and vice versa. So we can represent that knowledge as a Bayesian network as follows. The first option would be just what we have computed. If I know a, I can predict b and c in an independent way. So the best prediction of b and c given a is a times 1.5 for b and a multiplied by 2 in the case of c. So this is the model, 1.5a to a, and the residual thing that a cannot predict is something of variance 5.5 and 12 arising from these expressions here. But as correlation does not imply causality, this would be the Bayesian network adapted to the case that my input to my statistical inference is a. Even if the structure of the correlation is what we have, if in a particular problem my input variable, the thing that is known, measurable, is b, then I can reverse this arrow with no particular problem because we are not implying any cause-effect relationship. So if I now consider a second modeling option like here, then we will compute the best prediction of things given b, and for instance a given b has a coefficient of 0.3, so I can say that a is 0.3 b plus some stuff of unknown things that b cannot predict about a. This stuff can be modeled as, let's say, an additive noise of 1.1 variance. Of course, maybe the true life physics is not this linear relationship, but okay. As we are discussing on making linear predictions, the best linear prediction of a given b is 0.3b, and it will be wrong with this variance, period. What is underlying in the data that allowed me to compute the variance? I don't know, but I am restricting myself to what linear predictors can do. Okay, so this is the model of a, and of course, as the relationship of b and a once a is known is independent of c, then the arrow from a to c is left unchanged. So I put here this model exactly in the same way as in the option 1. So you can check, for instance, that indeed, if I multiply b times c 0.3, I get the prediction of a, and of course, if I multiply this thing by 2, then I get this 0.6b, which is the concatenation of these two linear models. And you can check that if b is something of variance 10, then propagating variance will also give us variance 2 here and variance 20 there. Indeed, for instance, the variance of 0.3b will be 0.3 squared multiplied by 10, which is 0.9. So when I add 1.9, I get the original variance of a, which is 2. Here we have it. So, as I said, when this input has variance 2, this model explains the whole covariance matrix we obtained. And in option 2, when this input has variance 10, it again explains everything in the 3x3 covariance matrix. As a last option, I can invert the arrow between c and a. So if I had an input c which was measurable, I can just do the reverse, and the best prediction given c is 0.2. This is the best prediction of a given c. So again, if I multiply 0.2 times the 1.5 prediction of the first option, a to b, then I get this 0.3, which is the best prediction of B given C. So I can change the predictions, and again, if this is variance 20, I can regenerate the whole covariance matrix. Okay, what's missing is kind of what to do if I know B and C. Okay, then in that case, well, I need the whole best linear prediction formula, and I cannot split my knowledge into independent arrow, let's say. So if I have B and C, I get a better estimate of A than in the case I have only B or only C. So in this case, the conditional independence concepts are of no use if I have two inputs. So our digression here goes on three Bayesian network models in which I have a single input, either A, B, or C, but the explanation of the relationship between the three variables can be split into arrows in these Bayesian networks. Okay, so let us conclude. In this video, we discussed the conditional uncorrelation when the residual of the best prediction of some variables given and others was diagonal. This restricts the ideas on conditional independence to the case in which we are wishing to make linear predictions. In the case of conditional uncorrelation, we were able to explain the whole relationship between A, B, and C when I had a single input variable in a sort of two independent sub-explanations, two independent arrows, conditionally independent given A. And we have this option, or also we could, reverse the arrows and get different representations of the same probabilistic model relating A, B, and C. So this is it. Thanks for watching, and consider subscribing if you wish to keep updated. Thank you.